course. Okay, and since we are before the lunch, I will be very quick. And so I have been discussing the topic I'm going to present with my long-standing collaborator Tadashi and the people at UIUC, and they also people here from Stanford in the audience. So I think by now, I don't have much need to introduce tensor networks, and I'll skip the things, and I just want to mention that I mentioned the quantum entanglement comes from this bond when the tensor network, and surprisingly I use the same notation as Mike for the dimension of the bond chi. Okay, so here's the. Okay, so again, I will talk about the particular kinds of tensor network, which is the MERA tensor network. And just again, a few quick words about the two kinds of tensors. One is the tensor with 3 legs that do basically decimations. But to represent a quantum ground state phase 3 or accurately, we need these 4-leg tensors, which basically untangle the quantum entanglement encoded in the target state. So so here's the kind of holographic view we are discussing many times, emerging from the MERA tensor network, and that was first discussed by Brian. And as Mike beautifully explained, the way we count we estimate the entanglement included in the MERA tensor network has a very strong resemblance with the way we compute entanglement entropy in the holographic setting. So that's motivate us the conjecture that MERA may be a concrete, discrete realization of holography. Okay. So this idea has been developed since then. On the MERA side, MERA has been applied to many systems, frustrated magnets, and also systems with potential with Fermi surfaces, which may have more entanglement than the entanglement in conformal field theories, and the other systems. And quite few times, MERA always challenged with other method, and in quasi 1D, I guess other method may be actually better, but MERA has this merit of representing the idea of renormalization group in the quantum many-body physics sense. Okay, so today I will talk about the very simple example of MERA, which is basically just a free field. And that's perhaps will be a good thing to look at to settle some questions raised previously. So I will first describe a free field construction, a free field theory, MERA for free field theories, and I will describe finite temperature and the application to a little bit more complicated of states of matter, which is topological insulators. Okay. I will be using a particular representation of MERA, which is technically convenient for me to manipulate things. So I will use the continuum representation of MERA. So I have a state which I want to phase 3 represent by using MERA. So that is the target state. And target state may be a ground state of the system, or maybe ground state of conformal field theory, let's say. And I will have a state which I will call reference state. And this reference state will be chosen as the state with is essentially no entanglement. Okay. So I start from there are two points of view. I can start from a reference state, and I act with a MERA network, which represents some sort of unitary evolution. And hopefully that may bring me a state I want, which is a target state. Or going backward, I have a target state and I want to systematically reduce the number of degrees of freedom and entanglement to eventually get a state with no entanglements. So motivated by the lattice MERA construction, in this continuum version proposed by Hagemann et al., we have two parts. Okay, so the first one, represented by L, does the spatial dilatation. It's not a space-time dilatation like in conformal field theory, but it just dilates in space coordinate. And there's the other part which take care of this four-leg tensor part of the MERA. So it is supposed to remove entanglement encoded in the target's ground state. So these three elements, actually maybe two elements, the choice of this reference state and the MERA network itself. Here it is represented as a evolution operator. And by choosing these two elements, nice way, we want to reproduce the target state. Pictorially, it looks like this. So I put my state of interest here in this coordinate, which I call U. Okay, and I put my reference state here, and this is just my choice of convention. Okay, and this U operator U, which I call MERA evolution operator, acts on this state along this line. Okay, so at this UV, which I conveniently choose to be 0 here, I have a target state with many entanglement and with many degrees of freedom. But by acting with U, I remove degrees of freedom as well as entanglement. Or, as I said earlier, starting from some trivial state. Acting with this MERA evolution operator U, I systematically add entanglement into the state, into the system, and eventually I want to get the target state. Okay, so that is the kind of cartoon picture of the continuum MERA construction. So I want to do a simple example of this construction. So let me take free fermion, Dirac fermion theory in 1+1 dimensions. And we know what ground state is. So ground state is annihilated by a particular combination of fermion operator where it is denoted by psi tilde. And the psi tilde is different from this original fermion operator psi. It is the one which you get from the original one by unitary rotate these fermion operators. Okay. On the other hand, so this is so for this case, of course, we can solve it. So we know the target ground state. Okay. I choose I choose a particular IR state. Which is this state, which is annihilated by psi and annihilated by psi to dagger, which is the component of this Fermi operator. And this state does not have any entanglement. You can think of this a reference state as a ground state of this part of the Hamiltonian alone. You make mass so large that overcomes the kinetic term completely. So there's no spatial correlation in this IR state. So this is a state as example of a trivial state, which I want to put at the IR. Okay. So fixing IR state, what we want to do is to find a operator which evolve this IR state into the ground state I know. Okay. And as I described already, this evolution operator has two parts, one denoted by L and the other denoted by K. And L basically just do spatial dilatation. So if you believe me, this operator just changes just rescale the spatial coordinate or momentum coordinate. Since it is a free theory, I will assume this MERA evolution operator, in particular the entangler part, is quadratic in field operators, okay, because everything should be solvable in free field theory. So it's quadratic, and it depends on momentum as well as u, which is the coordinate in the vertical direction or bulk direction of the MERA network. And for this particular case, I can take a certain assumption. I mean, this is actually not my assumption, but this was the originary assumption taken by Haigamato. Okay, and the idea is that this G essentially implements unitary rotation. Okay, so if you have a free field theory, by rotating your basis a proper way from, let's say, psi 1, psi 2 to psi 1 tilde, psi 1 tilde, psi 2 tilde, you essentially solve your theory. Okay, but here I'm interested in using MERA to solve free field theory. So in this case, what this entangler does is to act with this unitary operation successively. So, okay, so there's this series of unitary operation. At each time, I rotate my fermion operator in the right way. Okay, and repeating this unitary operation many times, we eventually get the correct fermion ground state. Okay, so this is what this cutoff function does. Okay, each time I do a unitary rotation successively. Of course, as I said, it's a free field theory. So if you want to solve your theory, you can do unitary rotation all at once. Okay, but as exercise, I'm following the MERA prescription. In that case, I do this rotation successively.
Do you expect these operators to be approximately local in position space?
That's a good question.
Are there polynomials in K except for capital gamma?
Yeah, so this part is certainly local. This part is a cutoff function, so I think it's still local. And you can certainly add more polynomials, but let's say I will stay in the local form of the. I'm writing everything in momentum space, but I want to follow the lattice construction as much as possible. But yeah, okay. So here everything is set it up. So I should say this correctly reproduce the free fermion ground state. Okay, but you still have to determine chi. And chi, for example, can be, well, in this case, you can solve your theory, so you can determine chi, but for example, you can determine chi variationally. But in this case, either way, anyway, you get the exact expression for chi. Okay. So we can solve certainly a free field theory by using a MERA construction. But now we want to talk about the structure of MERA network we have. It's written in the evolution time as an evolution operator, but we want to pick up some metric which tells you the properties of a MERA evolution operator or MERA network. So it may in principle differ. I mean, it differs from problem to problem. But I want to study possibly a space-time which may emerges from the MERA construction. So to talk about the possible space-time, or actually just space structure, I want to pick up some metrics. So here's just the one proposal, which is does what I want to see, but it may not be the unique solution to this problem. But I mean, I define my metric this way. So for any given two states, we can define a distance between two states essentially just by taking overlap. It sets a distance between two quantum states. If you have a series of states, so let's say parameterized by some parameter psi, we just take an infinitesimal version of this distance. And since you have a distance, you define a metric. Okay. So this is just the a definition of metric which works for any quantum system. Similarly, you can define connection by taking the overlap of two states, but in this case, I expand up to a linear difference in the parameter psi. So this is the very general way to introduce a notion of distance and connection. And this can naturally be applied to MERA construction. So we have a set of states now parameterized by scale u. Okay. Each time you act with a MERA evolution operator, you get some state. And you have a series of states, each represent a state at a different energy scale. So by taking the overlap, you can define some sort of metric. Okay, so as I said, this may be a metric which may be applicable, the proper one to discuss holography, but this may not be the only one. Okay, but just as a curiosity, okay, so let's say we define metric this way. Take the MERA state at scale u, and I compute the overlap between two states defined for different MERA energy scales, and I just define the metric this way. This is I think it's a good guess, but it's certainly motivated by the following observation. Again, coming back to the estimation of entanglement entropy, because entanglement entropy should know about the distance in the bulk. So let's say for simplicity, I cut my network in two halves. In this case, my entangling surface cuts through many bonds, many unitaries for like tensors. And the entanglement is directly related to the strength of the bonds, okay, times up to some scale factor. So something we defined as a distance or area along this direction should be related to the strength of the tensors that we put in the network. And this seems to be a way to capture such tensors. Okay, and the similar, I think you can have a very similar structure in the canonical ADS-CFT example. So I have a metric here appearing in computing the entanglement entropy. Okay, so this is the metric I introduced, but it does what we want to see. For example, for the case of free fermions, we can compute, as I said, chi u. We can determine chi, which sit in the MERA evolution operator, in such a way that it reproduces the fermion ground state exactly. So this is the form of the chi u. From that, we compute the metric GUU, which is the metric in radial direction in holographic language. And if I plot this metric, it does something like this. Okay. So first of all, I'm studying a massive theory, but I can send mass to be 0 to reproduce conformal field theory. In this case, I get the metric which is constant in this coordinate system, which is actually what we expect from the ordinary ADS-CFT setting. So this is the form of the metric I have in mind, and if this is constant, this represents conformal field theory. But we have also the state which is massive. If I don't turn off the mass, I have a massive theory. And in this case, what happens is that as MERA evolution operates, it removes some entanglement. Okay. But at the mass scale, state doesn't look like entangled anymore. So the MERA doesn't have to remove entanglement at the mass scale. So eventually, the strength of this entangler or disentangler reduces to 0. So no entanglement to remove, and the metric is 0, so there's no space. Okay, in this metric. Okay. Another thing, another exercise we could do is what about finite temperature? Okay. So at finite temperature, a natural way to think about is to take some field double, which we already discussed again. So in the MERA tensor network language, I take 2 copies of MERA tensor network, because I'm doing doubling in the thumb field double sense, and I can combine them in some way. So for example, a free boson or free series, I can write down a state living in a bigger space. In the double Hilbert space to reproduce the thermal state in the original Hilbert space. So here's the kind of a schematic. So I have a double Hilbert space, have some coefficient. But if I trace out one state, I get a thermal state, which is the original thermal state, which I want to represent. Okay. So can I build a mirror for this thermal state? Okay. And it is the mixed state, but once I double, I'm dealing with pure state. Can I construct MERA for this state? Maybe somewhat interestingly, or maybe that's we already expect, but this problem of constructing MERA at finite temperature is actually related to the different problem, which is the quantum quench problem. Okay, as it turns out. So what is a quantum quench? It's a time-dependent problem. So I start from some Hamiltonian, but at time t equals to 0, let's say, I suddenly change my Hamiltonian. So in this setting, I start from, for example, I change mass as a function of time. So here, let's say mass is finite or big, but eventually I switch off mass. So it's a quench, and I quench into conformal field theory. Okay? So this is a quantum quench problem. Okay? And as it turns out, you can view this quantum quench problem as introducing a boundary in conformal field theory, which was first pointed out by Krabras-Riccardi. So following their prescription, we can write down a quantum ground state at time equal to 0 as a conformal invariant boundary state in conformal field theory, which for the case of free boson looks like this. Okay, so we first solved the MERA construction for the quantum quench problem, which is again possible. But as you can see, the states we talk about in quantum quench and the states we talk about in double field theory are very, very similar. Okay. In fact, here I have a operator coming from one Hilbert space and the other operator coming from the other Hilbert space, but simply replacing this tilde operator into the ordinary operator, I can map this state into this state. So by solving quantum quench problem, I can also solve the finite temperature MERA construction. Okay. I just want to show you. Okay, maybe I'll just skip. Okay, so I can construct quantum quench by MERA, and you can believe me, perhaps it's a free field theory again, and this nicely agrees with what we expect from ADS-CFT. So this is the double-sided black hole, which showed up a few times already. So this is a finite temperature state. This geometry is representing a finite temperature state, and this state you can also get from some field double construction. So starting from some Euclidean solution, you can sort of analytically continue into this geometry. The corresponding state is the sum field double living in here, and they are coupled together. 2 years ago, I guess, Hartmann and Marcina proposed the holographic dual of quantum quench, which is just the half of this space-time. This is exactly what we did in the MERA description. Again, finite temperature and the quantum quench. Again, this is the exercise in free field theory, but this seems fit quite well with what we expect from the holographic way of thinking. Okay, so like how many minutes left?
Maybe 5 and then questions.
Okay, 5 minutes. Okay, let's say, so far I have been discussing free field example, and it seems like free field, although they are free field examples, we see some kind of evidence that there's quite a lot of similarity between field theories and the holographic descriptions. But now, as we have been discussing, question is, can we deal with something more complicated? Okay, certainly we can deal with complicated 1D Hamiltonian by using computers, for example. But to get some more intuitions, I will do the following thing. And this is again, this part is perhaps a little bit conjecture, okay? But as we have been considering a generic construction of MERA for generic conformal field theory, let's say, what we can say about this. So again, MERA network consists of two pieces: the choice of reference state and the choice of MERA evolution operator. So rather than solving both, I just focus on I just talk about the choice of IR state. Okay. So for the free fermion example, written in terms of chiral basis, this reference state actually takes essentially the form of conformal invariant boundary conditions. Okay. So omega can be thought of as a boundary states in conformal field theory, which are, for some people, it's a familiar object in discussing boundary critical phenomena. Okay. So if you think about boundary states, as it turns out, has a maximal entanglement in left and right moving sectors of the theory. But if you think about the entanglement included as a real space correlation, boundary state essentially has no real space entanglement. Unlike CFT ground state, boundary state doesn't support the entanglement, which scales as a separation of two regions A and B. Doesn't scale as the size of the region A, which appears as a bipartition. So it seems that boundary state may be a good candidate to take as a reference state or IR state for generic conformal field theory. This is just a proposal, but it is true that boundary state doesn't have much entanglement. Okay. But there's another piece of MERA network which I have to construct. So I have to now evolve from a boundary state into a ground state of conformal field theory, which I don't know how to solve it yet. But I can certainly consider at least smooth way to connect boundary state and the ground states of conformal field theory. So I just evolve with the Hamiltonian, which Shaoran actually already mentioned. So we just let if I just do an imaginary time evolution, because Hamiltonian eventually select the ground state, we eventually get the ground state Hamiltonian. The kind of the thing which looks quite different from the ordinary MERA construction is that this operator alone is not a unitary, so you have to rescale each time you operate with MERA evolution operator. It's not conserving a norm. But I just want to do a simple exercise. So at least in this way, I can connect boundary state and the ground state of conformal field theory. And following the recipe I talked about, I can define some sort of metric. So I can compute this overlap between states at different MERA energy scale. And at least the end result is what we expect. So in free field theory, in D dimension, this metric goes like volume of the system divided by some cutoff up to the exponential du. D is the dimension, and the u is the MERA scale. In 1+1 dimension CFT, we have essentially the same structure except central charge is appearing here. So that's roughly what I expect. But as I said, I don't know if this is what is really like MERA for generic conformal field theory. But I think as IR state, a boundary state is qualified as a good reference state to build a MERA construction. So I guess I don't have much time. So maybe I just skip here. And for free field theories, we see some features which are very similar to holographic consideration, maybe which we shouldn't expect because we are talking of free field theories. But nevertheless, there are very striking similarity between free field MERA and the ordinary holography. So to solve to construct MERA for more complicated interacting systems, which is necessary if we want to study a condition for which the holographic dictionary works, like large central charge, the gap in the scaling dimensions, and so on and so forth, or maybe the emergence of locality, which may happen in the proper limit. We want to have MERA constructed for interacting systems. Okay, so I don't think we have a very concrete result yet, but boundary state as IR state may be a good start. So that's my conclusion, but that's also the question to you, because that's something we have been discussing. So what is the generic construction of interacting conformal field series using MERA evaluation? Okay, thank you very much. I stop here.
I can't resist asking you to say a couple more sentences about the last point there, topological phases.
Right. So I have been discussing IR state as a completely entangled state. But when it comes to topological phases, there's a kind of question: can I really use completely uncorrelated product state as a ground state? Because after all, the definition of topological phase is that it cannot be connected to trivial state by using local unitary transformations. And in fact, if I just take simplest topological insulator and I just run MERA method, so this is the example, simplest two-band, two-dimensional fermion model, which shows topological properties. If I just run MERA procedure, what I found was that it is not possible to use product state as an IR state. Then you will fail miserably. Okay. So what happens is that I compare two states. So this state, I hope this notation is clear enough. So I have two bands, like psi 1, psi 2, as in my 1+1D example. And I fill all second states. And I just take this as the example of trivial state, no special correlation. So if I take this state and I compute the distribution of Berry connection, or rather the Berry curvature, which I already defined, it doesn't reproduce the Berry curvature of the target state. So we fail. If we replace this kind of naive guess by something a little more complicated, so it has winding, as it turns out, we can reproduce a Chan insulator by using MERA. And here's kind of picture of not the metric, but the flux. So I would say perhaps another motivation to think about this kind of model is that if you think about holography, it's not just a metric, but there's some charge field in the bulk. So topological phase may be an interesting venue to study the role of charge field. But for the case of trivial bulk state, the Berry flux essentially gets reflected back somewhere. And the total Berry curvature at the target state turns out to be 0, which we shouldn't, because we want to get a topological phases of matter which support non-zero Berry curvature. If I choose this state, this flux line coming out from the target state kind of absorbed into a reference state living at the IR state. So that's what I meant by a topological phase may be related to some charged object living in the bulk.
So that suggests if you took a quantum spin Hall state or something where the net Berry curvature is 0 effectively.
Right. So we haven't tried, but maybe there's some symmetry restrictions if I allow.
So if you allow the mirror to break T.
Exactly, yeah.
Other questions?
I have a technical question. We'll go earlier to the part about the metric for thermal double state.
Mm-hmm.
Sorry, can you go through?
Okay.
Just that, no, just the one with the metric. No.
Okay, so this is the metric for quantum quench.
Sorry, I mean the thermal double state.
Thermal double state. That's the same metric as this, because we use the same. We essentially use the same disentangler for both for quantum quench and.
You got a different metric, right? You got a metric that's exponential in 1/beta. That's the one I was getting for. So after this.
After this, okay.
After that. No, sorry. More.
More.
Yeah, so I didn't
Okay.
understand why the metric is exponential of L or beta. I mean, it's not obvious from the integral.
You mean here? Oh, sorry. Yeah, this is supposed to be just the integral.
If I naively do that, I get a 1 over, I don't get the exponential.
Why not? Because I have E here. E here, and it's integral from 0 to. I thought this is right, but maybe I'm wrong.
I can't solve the theorem, but anyways.
Yeah, I cannot do this in my head. Yeah.
It's 1 over x.
Sorry, that's the technical one.
Shinsei, you have this reference state for your topological phase.
Yes.
Go to that slide.
Sure.
Small trivial reference state looks singular at the origin.
It's very, very singular.
You took some specific state, right?
Right. I took specific state, and I don't fully. Okay, so I have to say I don't fully understand the nature of state. It's singular. It may be actually gapless. Okay. But so far this is the one possible state which we found we can use to disentangle topological insulator. But there may be a better candidate which avoids singularity. I don't know.
I just pointed out on the lattice we have exact
That's right. I should mention that. Right.
the chiral state to a product.
Right. Yeah, I should mention that. Actually, it's in here, but I skipped that. So sorry. Sorry. Yeah.
We'll have you getting hungry. If there are no other urgent questions, let's thank Shinsei first.